Achieving optimal health and self-realization in the modern world involves more than just diets of our food and exercise. It requires a new relationship with light, externally and internally. Welcome to the Light Diet. Thanks for coming on, and I'd love if you could just start by sharing a bit about your background from your experience, where you grew up, how you came to be in the United States studying, and some of, that detail.
Sure. Thank you very much again. After this podcast, you're never going to look at carbohydrates again as food source. So, because I'll convince you for good, we're going to return. But anyhow, so as you know, I'm Hungarian. I was born in Hungary in 1962, and I finished medical school there. I got my medical diploma in 1987, and I'm the 11th physician in my family. It's a tradition. Yet I decided to pursue science and to teach medicine or medical biochemistry. Medical biochemistry is my field, and this is how I connect with various clinical translational challenges and colleagues. And this is why I contribute in a certain way, because biochemistry is not very common nowadays. It's more of a genetics-based medical kind of treatment modalities are developing, yet biochemistry seems to be just as important for the better part. It seems that we do have to go back to some old metabolic biochemistry-related processes to understand disease better and to develop better treatments and integrative treatment options for patients. And I do teach and I do research for the field. I don't directly deal with patients. That's the work of the clinicians. Yet I do position new biochemical related ideas in mainstream medicine simply through activities that I do as editor of newspapers. Some of them are clinical newspapers, and also as a basic scientist. I do study biochemistry seriously, just simply to connect with applied medicine and standard medicine, or hopefully this knowledge will become part of the everyday medical thinking. I do work with stable isotopes, which are part of our physiology and biochemistry, simply because they exist. They actually function in our body in certain ways. And one of these isotopes or isotopic pairs is deuterium and hydrogen. And we're going to describe those elements a little bit with more details shortly. But before I would do that, I'd like to continue with my background. So I got my medical diploma in '87. Then I moved to to the United States in 1990, and then I moved to Los Angeles, California in 1998, when I became a faculty member of UCLA and School of Medicine, and I'm holding a full professor position in the adjunct series since 2015, and I did in the last few years. I did a lot of editorial and review type of work, reviewing biochemistry-related information, especially for journals like Nature, Scientific Reports, Medicine, Oncology, Clinical Oncology. I'm one of the editors, and also for Metabolites. These are journals that have very good translational and basic science narratives. They do have a open access publication platform, and their editorial work is very much related to deuterium, hydrogen, biochemistry, metabolomics approaches, which are not conventionally considered as part of genomics, or not necessarily just genomics or genetic profiles are presented or discussed in these journals and publications. And what's also very helpful is that now we are able to use original data as part of the review and the rebuttal process to introduce Deutenomics into the knowledge base of clinical medicine, because we can look at original clinical problems that are presented in these papers. We can look at original data to find out if there is any deuterium or deuteronomics related discussion to be placed in the paper, and then we can connect with clinicians through clinical scenarios that are interpreted from the viewpoint of deuterium or deuterium load or deuterium biochemistry in these clinical scenarios. And there are three major disease areas where we could actually show the benefits of deuteronomics. Deuteronomics is practically the science where we look at the isotope effects of deuterium or heavy hydrogen. And we're going to describe this with more details, but practically colorectal cancer, paraffin, embedded tissue samples, rare childhood tumors, lung cancer, and breast cancer are the major clinical areas where actually we could use deuteronomics as very critical basic knowledge to understand, enhance these disease therapeutic options. Obviously, we work with integrative doctors very extensively simply because their use of this deuterium or deuterium depleting type of science is very critical because it belongs more to the integrative arena of therapies, because this is a nutritional approach after all. So this is not a medicinal approach, but more of a nutritional approach to deplete deuterium in a human body. And we provide basic biochemical information of how to do this efficiently, how to do this safely, and how to do this as an integrated approach in the current standard or naturopathic treatment regimen, simply because we think these are very substantial parts and these are very substantial additions to current medical efforts, especially when we treat chronic degenerative diseases and more like population diseases like diabetes, obesity, cancer, degenerative diseases. In those disease areas, deuteronomics or deuterium depletion, they all come handy.
This is very, very scientific, which I think is good because I want to have a scientific audience. That's my goal here. So why don't we start from the beginning when it comes to deuterium? Thank you for sharing that, by the way. I'd like your explanation of what is deuterium and where do we find it in nature and why is it relevant? I think I could answer all these questions sufficiently because I've listened to you talk probably dozens of hours on your various lectures, but I'd like to hear your take and then we can dive deep from there into the relevance.
Sure. There are some new developments, but let's just start at the very beginning. So if you look at the periodic table, to the upper left corner, you're going to see hydrogen, which is the first element of the periodic table. Hydrogen is the lightest, the smallest, and the most unique element on our planet and in the universe, simply because it has one single proton in the nucleus, and this is the smallest particle that has mass, which is not decaying after all, meaning that it's a element, an atom that is stable and present in our universe generally, and it is actually the most common element in our universe. That's practically hydrogen and the proton. Proton is a hydrogen nucleus without an electron. And it has a positive charge, and it has a atomic mass unit of 1 Dalton. It's actually the foundation of all other elements as far as its nuclear structure is. So the first, the smallest, the most movable, the fastest moving, it's more like a ping pong ball when you look at sports, comparing all the sports that are played with a ball. It's actually like the ping pong ball because it has the fastest, the smallest stable. It's actually the most dynamic participant of our inorganic realm. Now,
may I just interrupt and ask here? So, from a biochemistry or physics standpoint, an electron is considered matter, correct? Or is it more considered energy? Is it sort of on a fine line?
Yeah, it's a very good question because simply electron has no mass. So we do not consider electrons atomic constituents. Simply, they're part of atoms, but they actually carry only charge. So the smallest element that has a mass is actually hydrogen, or the proton from hydrogen. Electrons have no mass, but they have a negative charge. Every proton that has a positive charge has to be surrounded with an electron which has a negative charge to actually balance the charge state of atoms. And electrons, by definition, are more like subnuclear or subatomic particles, simply because they only carry a negative charge in a wave form. That's why we don't really know exactly where electrons are, simply because they are always moved their location. Practically, they actually behave more like a negative charge cloud around protons. Now, the proton has both an elemental charge, which is a positive charge. It has a 1 Dalton mass unit, atomic mass unit, and it also has a location. So even though it moves all the time, you can, by its move, you can actually move protons, and this is what is the technological necessity to generate a nuclear magnetic resonance picture. You actually move hydrogen, you move protons to actually be able to determine chemical composition. And this because of the magnetic charge of protons, you can actually move protons in electromagnetic fields, and as a result of that, you're going to measure electromagnetic frequencies as these protons move around in magnetic fields. So the smallest one of all the elements is hydrogen, or the proton, and its natural stable isotopic pair is deuterium, or deuterium, which has no electron. We call it deuterium, and if it has an electron, it's called deuterium. And it's a very unique isotopic pair because the mass difference between these isotopes is 100%, and the size difference is also 100%, close to that. Practically, it has a proton. Deuterium has a proton and a neutron. And because the neutron and proton weigh 1 Dalton, it's 2 Daltons, and it's a significant, it's actually a large change in nature as far as isotopic pairs go, simply because hydrogen is the only element that has a stable isotopic pair, which is twice and double the size of hydrogen itself.
So if just to kind of add to the point there, if the proton were in a situation where it had to move like water, for example, could you compare deuterium to be like liquid lead almost in a relative scale?
Yeah, it's a good analogy. It's like a medicine ball compared to a football, or like a tennis ball compared to a ping pong ball. So you can imagine how difficult it is to handle something as twice as heavy in nature. I mean, if for example you have a car and you have to drive a twice as big car tomorrow, you have to drive a truck. There's no gradual, there is no easy handling of something as twice as heavy, twice as large. And they are actually isotopic pairs, so they would participate in the same chemical reactions because of their proton charge. And practically, it is like trying to play ping pong with a tennis ball or trying to play tennis with a football. So it's practically impossible for biology to handle the heavy isotopic pair of hydrogen through all the energy producing processes, through all the chemical reactions, and through all the reactions that hydrogen would take place, or all the chemical bonds that hydrogen would form. Deuterium forms chemical bonds that are actually 7-8 times harder to break. And it's because chemistry works this way. It's practically because of the close proximity of those atoms to each other. These kinetic isotope effects go very far of modulating or modifying chemistry or organic chemistry or physiology or biochemistry. And for this particular matter, hydrogen and deuterium has a very unique role in biology, simply because deuterium has to be discriminated, has to be filtered out from almost all procedures or all processes where hydrogen takes place or hydrogen is participating in the process. So practically, deuterium depletion or deuterium discrimination is a constant obligation of nature to take care of biological systems without breaking them down. And this is why Deutenomics, how nature handles this heavy isotope of hydrogen in biological reactions and also in the physical realm or the physical world, it's actually a very significant scientific arena or scientific knowledge that is entering clinical and translational medicine as at a very rapid pace. And this is why we actually have this conversation to actually explore this somewhat further for your audience.
That's the goal. So I'm going to pause real quick and have this cut. I'm just going to plug in my backup charger. One moment. One other thing, Dr. Boros, can you hear me all right?
Yeah, I can hear you.
Oh, awesome. When you're, if you're with your mic, just don't get too close to it, because then when you say proton, it goes pop,
Okay.
So just, you don't need to be far. The cool thing is we can adjust and make it louder, but if it pops, you can't really get rid of the pop. But
how is it now?
Well, because it sounds like it's moving. It's not so good, but once it's still, it should be.
How is it now?
It's pretty good.
Protons?
Yeah, that's popping? Really good. Yeah, okay. Perfect. Yeah, it's just the proton, and we're going to say proton a lot. So
is it just sound, or it's picture too?
It is picture too. If that's I mean, we don't have to share the picture, but we can share it on YouTube.
No, it's fine. I just wanted to know. Yeah.
Okay. Awesome. All right. So back to it. Okay. So there's a lot there as it relates to deuterium and so on. For someone who isn't familiar with biology, even like to the extent that you are, because you're a lifetime, biochemist, you take certain things for granted maybe, but I think the average person maybe doesn't realize or consider that most of life is based on hydrogen. It's carbon and hydrogen and oxygen and so on. So when we're talking about deuterium, I'm assuming that the reason it becomes so relevant is because so much of our processes as a living organism are based on hydrogen. And so when deuterium comes into the mix, it creates some issues. So could we sort of start to get into, could you get into a little bit of how, first of all, where hydrogen is really relevant in a living organism? And I'm assuming you're going to talk about the mitochondria, but wherever it's relevant. And then how hydrogen's big fat deuterium big brother can get in and cause problems. And one other thing is that you mentioned football, and for the American audience, I think you meant soccer ball, because a lot of people will just think, if you compare a soccer ball and a medicine ball, that makes more sense than a football and a medicine ball. But anyway. Go ahead, please.
That's right. That's correct. So you have any particular, or I just need to talk about?
Well, I just mean in general. Yeah, could you just talk about how hydrogen is really relevant in living organisms and where deuterium takes its place and begins to create problems?
Yeah. So hydrogen is the in biology, hydrogen is the common currency of energy, chemical bonds, and flexibilities. And this is simply because hydrogen bonds and hydrogen bindings, both covalent and hydrogen type chemical bonds, are very important in maintaining protein structures, maintaining DNA structures. Hydrogen bonds binding the two helices of the sugar backbone molecules of DNA, for example. Hydrogen is very important when it comes to transferring energy from food to water and so on. And hydrogen is part of water, and hydrogen protons are moved very rapidly in our living biological system, simply because hydrogen is the way we generate energy, and hydrogen is the way how we generate chemical bonds most of the time. Hydrogen is also the most abundant atom in the universe in general, and hydrogen is also the most abundant atom in living system, in biological systems, simply because really the whole life scenario, life is nothing else but actually breaking water, carrying hydrogen on food, and carrying oxygen in air, and then unite these two elements again in a biological system to make water again while energy is produced. And hydrogen is very important, and its size being the smallest atom is very important because hydrogen can go through this proton or quantum destabilization process, especially in mitochondria, which is producing zero-point energy protons, which break up practically as part of water. And I'm going to talk about this in more details, but practically what happens to proton, it can actually go into a waveform in mitochondrial mitochondrial nanoconfinements, or small spaces in the mitochondrial cryptae. And simply because of this transformation of protons from an atomic state to a quantum destabilized state, it gives rise to a number of waveforms, a number of subatomic particles which have very short half-lives. And this is the reason why we can turn around and turn over so many protons or so many hydrogen during the day, for example, and use so many food-derived protons to generate ATP, because hydrogen can actually go through quantum destabilization phases when it comes to what we call nuclear quantum effects. And actually, they can be source of, for example, bosons, light, and quarks and subatomic particles, which is a part of translational medicine, part of medicine that we are exploring right now. So simply just looking at hydrogen, it is the cash, it is the currency, it is the most common, it's the common language, it's practically the most important element in biological systems because of its easy to transform, easy to move, with relatively small energy invested, and it can be very rapidly reactive with oxygen in mitochondria in using the electron transport chain and activating oxygen to react with hydrogen and form water very rapidly, or peroxide, which is again a very important source of what we call metabolic water or living water that actually keeps us alive and allows us to produce enough energy for our daily activities and sport activities, or maintain a differentiated chemical structure and a biochemical network that is able to discriminate against these isotopes of hydrogen and its heavy isotope deuterium. Now, deuterium cannot really produce all these. Deuterium cannot go through nuclear quantum effects. Deuterium is twice as heavy, twice as large. It cannot fit into certain intracellular protein tunnels. It cannot really bind to certain protein structures in the cell because deuterium would destroy them. And deuterium is not able to get through a destabilization process in mitochondria, and that means proton quantum destabilization may be compromised if there's too many deuterium in the mitochondrial nanoconfinements or the mitochondrial space, which takes place in the cryptate. And this is a very interesting process, and we have learned about this the last 6-7 months. How water behaves in mitochondria as part of the structured or the surface water compartment. If when water becomes structured or water becomes more surface bound, then hydrogen deuterium isotope effects become more dramatic. And when water is structured, because of these structures are disrupted by deuterium, deuterium is very devastating as far as mitochondrial and energy producing reactions go in our system. And deuterium is also very damaging when it comes to making chemical bonds or hydrogen bonds in protein or DNA or RNA or fat based cellular membranes, simply because it just cannot be chemically broken off from organic molecules as easy. Hydrogen can be broken off or removed during biochemical reactions. And because of these structural disadvantages that deuterium carries, being twice as heavy, twice as large, and not being able to go through these nuclear quantum effects or quantum destabilization, deuterium has to be discriminated or filtered out from certain biological processes like energy production, but it's also needed in some other processes, for example, cell growth, cell proliferation, and for example, in bacterial growth, and for example, in virus replication. And this is the type of argument, or this is the interesting, like now in the COVID kind of scenario, how deuterium affects the epidemics or pandemics that is currently taking place. And we can talk about that later, but practically just to answer your question, hydrogen and deuterium, because of their chemical and isotopic relationship, they actually have very different behavioral pattern in biological systems because of these isotope effects, which are more dramatic or more emphasized or more enhanced when water is structured, and mitochondria has only structured water or surface water. So for that reason, deuterium as a heavy isotope of hydrogen has to be discriminated from all mitochondrial functions, and it has to be regulated in cytoplasmic functions, and it has to be controlled to control DNA size and DNA-related replication signals, which we know prokaryotes and bacteria very much utilize for the continuous growth, and also cancer cells. So deuterium has a very unique role in biology. That is, it's unnecessary and has to be discriminated from certain processes, but it is necessary and important to cell proliferation and continuous cell growth, which certain phenotypes would definitely require. And we're going to point out those in our body. For example, you need deuterium for continuous epithelial cell growth in your gut. You need deuterium for continuous epidermal basal cell divisions to produce keratinocytes to actually produce skin and protect your body. Deuterium is very important. Deuterium is very important in your mucosal membranes to make bacterial propagation and virus propagation limited or advanced depending on the season. And deuterium needs to be filtered out from mitochondrial functions because it breaks mitochondrial ATP synthase or energy producing nanomolecules. So it's not an easy task to explain there's no general rule of how we process deuterium, but this relationship of hydrogen and deuterium always has to be considered as biologically relevant because we just need to know how much of deuterium we need to maintain certain particular or certain cellular phenotypes. So this is why this is such a large topic in its own scientific terms. Deutenomics just deals with all these important relationships that exist between hydrogen and deuterium.
This is awesome. So there is a lot there. I'd like to get into where, well, I think I already know the answer personally, but you can tell me if my thinking is correct. So my understanding is that deuterium is present in nature everywhere that hydrogen is present in varying proportions. Is that correct?
That's right. Everywhere where there is matter or there are atoms, hydrogen and deuterium almost entirely just part of the inorganic, and obviously the organic were, yet there are very few molecular or compartmentalized biological systems that do not use protons, or in a certain transition states they may be deprotonated, but actually protons are very reactive and they can bind to any element almost, and they are very general and very well distributed in nature. And where there is hydrogen, there's always deuterium. And their relationship is they are almost inseparable, yet for certain biological processes, they have to be separated. So you can imagine how difficult task it is to maintain this biological kind of checking mechanism to make sure molecules which not supposed to have deuterium don't have it, and molecules that are supposed to have deuterium and collect it for specific purposes, for example, by bacteria, then deuterium is provided for them. But practically, as you said, indeed, deuterium and hydrogen go together. Every 6,600 hydrogen has one deuterium in nature as a general idea. So in oceanic water, we know that the concentration of deuterium is 155 parts per million currently on our planet. That means every 1 million hydrogen would have 155 deuterium in the same atomic compartment. And this is too much for biological systems or for mitochondria. Practically, it has to be deuterium free. So this deuterium hydrogen compartment that we actually consume as water and food has to be biochemically processed, and deuterium routed towards certain chemical reactions and certain biological compartments, while hydrogen would participate in mostly energy production and making chemical bonds in proteins that are associated with mitochondrial and peroxisomal functions. In the meantime, deuterium has to be deposited into DNA if the cell is dividing, or it has to be disposed from the cell, removed from the cell through various mechanisms. And there are biochemical reactions that are specializing for these deuterium removal task and procedures and processes. But after all, looking at their natural abundance, 155 ppm in oceanic water, our own water that we produce should be less than 130 parts per million. And in mitochondria, if it's metabolic water, it should be deuterium free. So we believe that there is a huge gradient change as far as deuterium concentration go from oceanic water into mitochondrial metabolic water. And for that reason, all food or water that we consume, all liquids, have to go through several layers of biochemical protective mechanisms to actually remove deuterium from potential contaminations in food and biomolecules, to provide a clear deuterium-free oxidizable source of carbohydrates and fat for mitochondrial functions. And for everything else, where there are rapid cell growth or there are microbiome functions, then deuterium is necessary to maintain continuous cell growth and unlimited cell growth. And that's the case in mucosal membrane and also in the gut. So it's a very, I would say, distributed, dispersed type of knowledge throughout biochemistry, deuteronomics, and medicinal deuteronomics. This is a huge task to encounter and to understand all these processes with sufficient details that we can move clinical medicine. Yet this knowledge, this basic fundamental knowledge, is very important to address, for example, epidemics, for example, growth challenges, for example, cancer, epidemiological scale, population diseases, and so on. It seems that deuterium have a fundamental role in explaining and as therapeutically intervening with these processes, simply because deuterium is just one of these very curious elements that can replace a proton anywhere there are protons, yet it can destroy anything that a proton would keep together. So you understand the depth of the difficulty in this, and this is what biochemistry does to address these problems.
I want to get into that. So one thing, first of all, is you mentioned ocean water has a certain amount of deuterium, which is high for biological systems, or at least that's how I understood it. Do you think, just total side question, do you think desalinated ocean water as a drinking source is a very bad idea because they're probably not reducing deuterium?
Yeah, any water of environmental source is very tricky. Any water, desalted oceanic water is probably the worst water type where you can drink, because that's the highest concentration of a big water body on Earth, and it has the highest deuterium concentration as the largest body of water on Earth. And every water that originates from vapor and oceanic vapor, they are already lower in deuterium because of this physical fractionation process. So the highest water that you can actually obtain from natural sources in bulk amounts is actually oceanic water or river water. Their ppm or their deuterium content is somewhere between 145 and 155 parts per million. Human beings should only consume water when they are thirsty. It doesn't have to be water. You can actually eat fat to cover your water needs, and that's better because it has low deuterium. We're going to talk about this in detail, I guess, later. But practically, drinking water is really not without danger or harm or risk, simply because environmental water may contain too high deuterium to run your biological system safely. So usually I recommend that thirst is the most important and guiding signal for water intake, and it's should be just limited to just to kill your thirst. Practically, every other water source you should provide from ketogenic diet, natural ketogenic diet, or fat.
So can you explain, I definitely want to get more into the diet. I also want to get into our bodies, the actual mechanisms we have for checking for D, lots of different things here. But can you explain from your perspective why there's such a craze of hyperhydration and people recommending hydrate, drink half a gallon a day, half of your body's weight in ounces people recommend, take your, why do you think this is the case?
it has to be some kind of a commercial driven set of advice, simply because there is no reason to drink water more than you would need based on your thirst. And I'll tell you a good example. Obviously, eating, drinking, sleeping, and a few other things are basic instincts. And I never heard a doctor saying that, if you walk by a bed, why don't you lay down to sleep for 2 hours? If you just because you have water around, it doesn't mean that you have to drink it. Now you can get water from as a basic instinct. Sleep is just as important, but you don't go to sleep unless you are actually sleeping. And there is a period of the day when you actually go to sleep, and this is at night. And actually the process is just to deplete deuterium in your body. So loading your body with water all the time during the day through food and water is really physiologically or biochemically is really hard to explain why these recommendations and hydration protocols are so necessary. I don't think they are necessary. The problem is, if you drink too much water, you may dismantle the antidiuretic hormone regulatory system on energy production, nanomotor function, mitochondrial function, and sleep cycles, because they also have metabolic overarching with melatonin and so on. If you actually drink too much water, you suppress the antidiuretic hormone synthesis. You go into a state of diabetes insipidus, which is plentiful urination without sugar in your urine. You are actually constantly you're thirsty because you don't have antidiuretic hormone that can actually salvage water in your system because of the increased water intake. And antidiuretic hormone synthesis takes about 3 to 6 months to restore once to stop drinking excessively water. So from the biochemistry, from the translational clinical point of view, I really have hard time understanding why this recommendation is standing in the medical field to drink water excessively. It's like asking, again, somebody to lay down in the middle of the day just because there is a bed or a couch nearby and sleep a few hours because it's available. So it just makes no sense to me.
That's amazing. It's so interesting. So again, I'm going to just kind of rapid fire questions because I want to get through a lot of stuff, but this is also fascinating. So one, as it relates to that subject, is when we drink, I haven't had anyone be able to explain to me, just from my own research even, it's not very clear. Like when we drink water, where does it go? I mean, it's absorbed through is it absorbed through our stomach primarily into our bloodstream? Like where does externally consumed water go, and what does it even do in our body,
Well, it gets absorbed in the duodenum, so it's in stomach. The stomach mucosa is not an absorbing type of mucosal element or organ. Water passes very quickly through the stomach, passes to the small intestines, and the first part of it is called duodenum, and duodenum will absorb water rapidly, and it actually gets into your bloodstream. It gets into your portal vein, and the portal vein will take water in your liver, and it gets into the systematic circulation, and you urinate it out. So people who drink a lot, they also urinate a lot because their body may not need that amount of water simply because they get rid of it through a very easy process, and that's what we know, urination. And you probably observed this, and you know how you have to be careful when you drink before you get on an airplane, how much you can drink before you get it in your car before a long drive. You know these reactions or these consequences if you drink too much water. And that's practically the basic argument that I would keep clear, that simply if you don't need water and you drink excessively water, you will get rid of it. Your body has to get rid of it. And also your body would compromise certain water producing reactions, which are actually very important as far as your energy production goes. You probably heard of people who were saying that, I get obese and even if I just drink water. Yes, indeed. If you drink too much water, your metabolic water synthesis or metabolic water homeostasis will not be very well balanced. So you cannot really transport low deuterium metabolic water from mitochondria to the cytoplasmic space, and from the cytoplasmic space to the interstitial place, and maybe to the plasma, simply because you have excessively drinking water, and you are actually overloading your circulation with water, with external water, and you don't allow your metabolic water to dilute into this space with low deuterium metabolic water that's coming from mitochondria. Now, the amount of protons that you produce or you recycle every day, it's about 2,000 gallons worth of water each day. So we are talking about a significant amount of water or worth of protons that you have to recycle each day. So providing excessively water is compromising this water recycling, homeostasis.
Could you clarify that? So I remember you mentioned in another podcast, 1.5 liters is the amount of water the mitochondria produce in a day. Is that what we produce 1.5 liters? But you're saying the amount of protons that we turn over is the equivalent of 2,000 gallons worth.
2,000 gallons. So if
that's
you
8,000 liters approximately.
It's about 7,200 liters.
Yeah,
that's
wow.
Right. It's a swimming pool almost. I mean, a small swimming pool. So if you consider how much ATP we synthesize a day, how much energy we burn a day, from there you can calculate how much protons you transfer in mitochondria and how many mitochondrial nanomotors there are. An average calculation, let's say the human body has 70 trillion cells, and each cell has about 200,000. Each cell has about 2,000 or maybe 1,000, between 1,000, 2,000 mitochondria, and each mitochondria has about 320,000 nanomotors. We know this by electron microscopy and some morphological studies, and we do know for how much ATP we produce per kilogram of body weight. And we also know how much ATP we produce during certain physical exercise. So just looking at these parameters, just using these calculations, then again, it's not a short calculation, but we've done it, and you can look at those calculations in some of my talks. But actually, the amount of protons that we pass through the nanomotors each day to produce a certain amount of ATP is about 2,000 gallons worth of water. That's the 7,200 liters. Yeah. Now, this amount of water would be impossible to recycle in the tricarboxylic acid cycle or the Krebs cycle or Sangiardi-Krebs cycle. That's how we call it. So that's why we need this proton destabilization process. So you not only recycle water, metabolic water, but you can also destabilize the protons, generate vacuum, or what we call the quantum vacuum in your mitochondria, and your body is trying to, your life is practically nothing else as trying to fill this quantum vacuum in your mitochondria through proton destabilization. And this drives life practically always towards the direction of investing protons in mitochondrial ATP synthesis, because those protons disappear. Again, they don't disappear. They take a more of a vacuum, quantum vacuum, or more of a wave length or wave kind of form. But practically you can recycle, you can produce a lot of protons for ATP synthase functions, and then you can destabilize a lot of protons, simply because there are these nanoconfinements in mitochondria, hydrophobic nanoconfinements, which can actually decompose or destabilize protons and not deuterons. So this is where deuterium becomes so damaging, because it actually destroys two functions of the mitochondria, two main functions, ATP synthase rotations, and this quantum destabilization.
So I did not expect that we would talk about this, because I've never heard you actually talk about the quantum destabilization. So I'd like to get into it, actually, because it's something I don't know much about. So one first question is a basic biochemical question, because I'm not a biochemist by any means. I've read a bit, but not a ton. So inside of the mitochondrial matrix, where the Krebs-St-Georgi cycle, TCA cycle, citric acid cycle, which, by the way, if you ever get to speak with some of the higher ups in biochemistry, could you have them pick one name instead of three? Because I don't understand why they have three names for the same thing. It's very confusing. But anyway.
Actually, we like to use our names, which actually mean the same cycle, because the cycle has very many different roles in our life cycles, and it's really not a cycle. It's actually a reaction, set of reactions that can work as a cycle, but it can also provide and produce certain products that other cell functions can use.
So the tricarboxylic acid cycle,
yes,
the citric acid cycle, the Krebs cycle, the Krebs-St-Georgi cycle. So you got 4 names so far. Am I missing any others?
Hans Krebs was the German physicist biochemist who described the last 2 reactions of the cycle, which is malic acid and oxaloacetate acetate conversion. And he also described kinetics related to other reactions. And Albert St-Georgi clarified 4 of those reactions, including fumarate hydratase, which is one of the very critical reactions to recycle.
I just was writing that down because I wanted to ask you about that. That's so funny.
And,
anyway, continue.
And the tricarboxylic acid cycle is used because those actually have three carboxyl groups, those intermediates. And citric acid cycle is because the first reaction is citrate synthase. It synthesizes citric acid from oxaloacetate and acetic coenzyme A. So simply, all of these names pick out one of the main elements or one of the critical elements of the cycle itself. And this is why we like to use these names, simply because they all kind of describe the same cycle from a different kind of perspective, or a different main functionality that is related to the cycle. It's practically talking about the same Formula One race car, but somebody likes the engine, somebody likes the driving or the steering system, somebody like the computer system on the same car, but practically the same. It uses it actually just have, all of them are unique to the cycle. These
I
names.
see. So you use the Krebs-St-Georgi cycle because he's your fellow Hungarian guy, right? So you like to give him the credit.
Actually, I used the St-Georgi Krebs cycle because he actually, my grandparents knew him. So, and actually his Nobel Prize in 1937, because he described the fumarate hydratase process, because the fumaric acid is hydrated in the cycle, and that's how metabolic water is consumed, deuterium depleted metabolic water. And when this reaction is defective, then cancer develops because there is no metabolic water recycling. That's why his Nobel Prize was, actually he didn't share the Nobel Prize. He got his Nobel Prize as one individual, simply because his discoveries were so significant, and they still are.
That's amazing. I also want to get into that. So with where I'm going with that basic biochemical question is, when the basic biochemical or biology class, we learned that as electrons are donated from NADH to the electron transport chain, the electrons are carried across a series of, electron donors, the iron or Fe based proteins that, the electrons hop along the chain towards oxygen, where they reduce oxygen and they make the water. And then protons from the matrix are being pumped across the membrane continuously to create the proton gradient in the intermembrane space, which then drives the ATP synthase. So where do the protons in the matrix come from initially? Are they coming from food, or are they coming from water that we consume being broken down, or like where do those protons come from? The ones that are
they all
in
have to
play.
come. They all have to come from food. They all have to come from food.
Okay.
Your food comes down to three major substrate components. One is carbohydrates, which is carbon and water. That's why we call them carbohydrates, because carbon is dissolved in water. And if you look at the amount of carbons and hydrogen and oxygen, for example, in glucose is C6H12O6. It's actually six carbons and six water molecules chemically kind of mingled together. However, fat molecules are mostly hydrogen and carbon, so there's no oxygen in them. So it's not, we call them hydrocarbons instead of carbohydrates. Hydrocarbons are very hydrophobic. They form fat, they form membranes, and proteins or amino acids are in between because they also contain nitrogen besides the carbon and the oxygen. So these are your basic food elements, and these are your basic food components, and you only need hydrogen from these substrates to be carried to oxygen in the mitochondria to form water. And you said correctly, NAD or NADH carries the hydrogen and the electron to the electron transport chain. Electron is ripped off of the NADH or NADPH complex. Electron is ripped up with the hydrogen. The proton, this is how hydrogen becomes a proton. The de-electronized, or the electron, which becomes electric current practically, and it's going to form like a spark plug, like in a car engine, this electron chain. It's an electromagnetic ionizing force for oxygen. So actually oxygen is activated. It's an atomic form. So oxygen can form with hydrogen very rapidly water, which in nature we call it exploding gas, because elementary oxygen and elementary hydrogen, they are very reactive. That's why we can't really build hydrogen-driven cars, because once hydrogen becomes free in air where there is oxygen and there's a spark, then the explosion is huge. So those accidents would not be just property damage to the car. It's practically property damage to the neighborhood if that happens, because hydrogen is very reactive with oxygen, and oxygen is present in air about 21%. So because of this high reactivity of hydrogen and oxygen, protons need to be pumped in between the intermembrane space in mitochondria. And actually, mitochondria is the only organ, or the only kind of technological solution where actually you can generate a hydrogen gas fuel tank between the two membranes of the mitochondria along a gradient where protons or protons, because of their positive charge, they want to come back into the matrix and drive these nanomotors in the meantime. And that takes a positively charged proton to actually do that. And simply because of the nanomotors, electromagnetic forces, those positive charges, single 1 Dalton protons can actually deliver this physical force that actually spins these nanomotors, and we are able to assemble ATP, adenosine triphosphate, using inorganic phosphate and also ADP. And
so is that process like electricity is flowing electrons? Is that like protonicity in some sense?
No, yeah, there is electricity, the electron transport chain is practically a set of proteins with iron that can actually transfer electron from one place to another. So the last element of this electron transfer chain, which is cytochrome C oxidase, that's practically the complex 4, which has oxygen in a very highly charged form. And as protons, as they fall into the matrix, water is formed immediately at a very rapid pace. And because of this electron transport chain, you're able to generate elementary oxygen instead of the molecular oxygen. The molecular oxygen, the oxygen exists in air as O2, and it's not reacting with hydrogen. But once you charge and break molecular oxygen to elementary oxygen, it will have a very rapid, robust, and very vehement reaction kinetics with hydrogen, and water is formed instantly.
Yeah.
And you probably remember when you were in elementary school, your teacher collected hydrogen gas by electrolyzing water, and they collected hydrogen into a balloon, and they carried the balloon down to the gym. They called all the kids to stay in the gym and look at the balloon as the teacher was igniting the balloon with a candle on the end of a long stick, and all of a sudden this whole balloon exploded. That's how fast hydrogen reacted with oxygen in air. So it's called exploding gas. So this is what takes place in mitochondria. This is why we need the electron transport chain to activate oxygen. And it reacts with hydrogen very quickly, very rapidly, and it's almost like an explosion if it's uncontrolled. But in mitochondria, it's a controlled process, simply because the molar equivalency is important just to produce sufficient amount of water from all the protons that are coming in. So practically this is a very efficient, very robust energy producing system. You just have to use the kinetic reactivity of oxygen and hydrogen. In the meantime, you have to charge oxygen. That's why you need the electron transport chain.
Okay. So I think of it kind of like, if you have wood, it takes, you have to slowly burn the wood. You have to start with kindling and build it up till the fire is strong enough to burn the log. And then if you have like leaves, it's easier to burn the leaves. And then if you have gasoline, you can light it and it'll explode almost as fast as free hydrogen. And my understanding is because it's that the hydrogens are more accessible in some sense. They're easier to break off the carbon backbone as it's more and more refined. And when it's free hydrogen, it's just purely instant practically. Oh, yeah. There's not even a second of delay. Yeah. So with all that, this is fascinating, all of it. So with the proton quantum destabilization, I don't, how much time do you have, by the way, to speak? Because I can direct my questions based on that.
Yeah, I have the whole afternoon.
Okay, well then I won't. Again, we'll be efficient, but I want to get into this. So the quantum destabilization, I've heard enough of you speak about, maybe not enough because I'm still eating carbohydrates actually, but about how the deuteriums actually clog up those nanomotors, break the nanomotors, and damage our mitochondria. And that's something I'd like to get into, and how the implications of that on our life. I'd also like to get into the quantum destabilization, but we've moved so far into the subject. There was just two things I wanted to ask you about before we go any further, more about the history and the background of deuterium. So one thing is that I believe it was either you or maybe Dr. Robert Slovak. I imagine you're familiar with him, being another researcher in deuterium. At least I would presume so. But I heard a story from either one of you that was describing the initial discovery of deuterium depleted water with there were some Russian people who were found to have been living significantly longer than the rest of the Russian population, and they couldn't figure out what it was, and they determined that it was the deuterium concentration in the water. Are you familiar with that story?
The biologically relevant deuterium depletion scenario is coming from Dr. Gábor Somlyai. who was the first who used this in biological in vitro systems, deuterium depleted water, to actually address cancer cell growth. But before that, obviously, and Russian scientists have been pursuing deuterium research for a very long time, and they have observed, and it's part of their space exploration program as well. And it's a long-standing observation that people who actually live at higher altitudes, where deuterium is more fractionated, meaning that there's less deuterium in the environment, high altitude people, they actually live longer than the general population, for example, from the same country. And also, there are experiments and there are publications showing that in biological range, which is, let's say, from 155 ppm down to, let's say, 95 ppm, there's a clear effect of deuterium depletion in longevity, in slowing down cell proliferations, to slow down aging, to slow down mitochondrial damage or mitochondrial harm, and so on. And I don't exactly remember what story that was, and I don't know about any details of that, but I know many other stories, or very many other anecdotes simply reporting the same scenario. People who live in generally low deuterium environments, they actually have longer lifespans, and that can be shown experimentally too.
So that's very interesting. That is something of great interest to everyone who wants to live longer and be healthier while they're alive. So I remember when we were first in Vermont, there was a lot of things, when you and Dr. Kruse were sitting together at the dinner table, I just thought it was so funny because I had never seen him. I had spent some decent time around him, and I had never seen him get along with someone so well as you. It just as far as the way that you shared this information, and he was just really in line, because usually he is disagreeing with most of what most health professionals and food focused diet gurus are talking about. But with what you were sharing, it was like just pure fascination and interest, at least from my observation. And there was many things you mentioned, like, for example, that the reason flies eat poop or shit is because they use the deuterium in the poop to basically divide more quickly. And there was many other things like that. You also mentioned the book in the Bible, Deuteronomy, and how it has some relation to deuterium fractionation. And I'd love for you to talk about that, because that has fascinated me, and you didn't really get into too much detail at that time.
Yeah. So you want to hear about my relationship with Dr. Kruse or the Bible, the ancient?
Well, I'd love to hear about both.
Yeah. So Dr. Kruse, being an excellent surgeon, he is very educated and very smart, pursuing inorganic chemistry, or I would say medicine or medical physics, to support some of his initiatives and ideas. He is not in the academics, he's not in the publication, he's not in the peer-reviewed literature scenario or arena of performing or pursuing art. Yet some of his ideas are very close to what I actually position as a medical biochemist. And we can actually talk very efficiently about these overlapping scenarios, because he knows more about physics than I do, but he doesn't know as much biochemistry as I do. So we kind of complement each other in these discussions, simply helping each other just to gain a better or more thorough insight of our own fields. And when we actually talk, or when we talked, then we just explore these obscurities or ideas that we didn't know how to handle, how to explain. That's why we need more like consultations or discussions that enhance our own knowledge in our particular field that we perform. Yet, surely my medicine, my biochemistry background also allows me to look at ancient writings and kind of established how old this information is as far as reading ancient literature. And truly enough, the relationship between hydrogen and deuterium, like repeating something or giving a second emphasis or actually make it sure the change is significant and impactful, and that's what hydrogen deuterium have as a relationship. And biologically, it's very, very critical to know about this relationship between hydrogen and deuterium. I could look at old text or ancient text, for example, Deuteronomy, which is the fifth book of Moses. It's part of the Torah, and it's also part of the Old Testament. These are canonized writings. And the Greek rabbis, when the Torah was translated into Greek, the Septuaginta, the translation of the fifth book of Moses, captured this relationship between the laws and repeating, multiplying, doubling, explaining again the laws. So this carries this actually the same principle as hydrogen and deuterium. It's actually doubling something. And this is the weight and the size relationship between hydrogen and deuterium. And this is the role of the fifth book of Moses to double again the laws, the religious laws, practice. So this is why they call it Deuteronomy. Now, if you look at the physical characteristics or the physical scenarios that, as far as water is concerned, or water is discussed in the scriptures, in ancient writings, in the Torah and in the Old Testament, then you see immediately that actually everything that is described in the Old Testament and Torah as far as nutritional, physical phenomenon, they are all related to deuterium depletion one way or another. Some of them has some very important medical relevance. Some of them have very important relevance as far as physics is concerned, and some of them are very close to explaining some evolutionary and some cell division, nutritional guidelines just to control human population, to control human health, to control human longevity, and so on. And those descriptors or those stories or pictures that we can actually get from the Bible, get from old text and ancient writings, those are all related to Deuteronomics, how to control deuterium content in the human body, and how to, for example, pursue a lifestyle which is deuterium safe in ancient times when people supposedly did not know about deuterium. I think they did, not directly, but indirectly, and I think we do have these writings and information in human thinking and in human nutritional and health maintaining behavior, almost like our basic instincts, simply because they are so important. And definitely, even though we did not have in ancient times sophisticated physics, chemistry, and technologies that we now have, we have nowadays, we still had to get rid of deuterium. We had to deplete, discriminate against deuterium, and this is why all the kosher diet, all the dietary routines, all the farming procedures, all the stories in the Bible, eating fruits and getting kind of crazy, just like what happened in the Garden of Eden. Before God kicked out the first couple from the Garden of Eden, they ate carbohydrate-loaded, high deuterium, glucose-loaded fruit, which actually made them crazy. They started hiding, they started lying, and they started having paranoid thoughts. So everything that you look in ancient writings can almost certainly can be positioned or can be discussed from the Deuteronomics point of view, For example, if you look at Gilead, who took his army to fight Goliaths, actually he picked the 300 soldiers that didn't drink water. Simply they were just kind of wetting around their mouth, simply because, just like now in sports medicine, you don't want to drink water. Simply in a boxing game, they all spit the water out, simply because when it comes to durability, strength, and fit for a fight, you don't need to drink water. You practically need your low deuterium depleted water to function, to actually get the more strength from your muscles. These examples are all in the Bible. These examples can be pulled from the Bible and repositioned or explained again from the science of Deuteronomics, but they all serve one purpose, and that's a healthier, stronger, more able to focus kind of human phenotype or individual can be used for various purposes, like farming or overcoming challenges, or act in a social manner, or act in a religious group as a participating member of the society. So practically deuterium depletion is almost an ancient knowledge, and the technological details are revered nowadays, simply because now we have technologies that we can go after quantum destabilization of the proton, we can go after a certain phenomenon, and now the ancient writings become a different read, simply because now we understand why those events, why those stories, why those nutritional recommendations, why those examples are written in the way they are written. So we are actually translating the Bible again using Deuteronomics arguments.
So could you this is totally my own curiosity. Could you maybe give an example or two more specific from the Bible? Like for example, how does the kosher diet relate to deuterium depletion, or other examples you might make, anything you have in your mind? I'm super curious.
Yeah. So there are, I'm just going to bring, it's endless, but I just bring you two stories. If you look at the old, if you look at the Old Testament, if you look at actually Genesis, which is the creation, if you look at the first two sentences of the Bible, it talks about God's Spirit hovering over the waters. Now, we do know that anything in vacuum that hovers over water is deuterium depleted or deuterium fractionated water vapor. So this is how God identifies himself, as deuterium depleted water. And surely, as a physical phenomenon, I'm not saying God is deuterium depleted water, but in the text, he identifies himself for any human being. If he wants to find him, then it's going to be in the form of a water vapor floating over the surface of the water, which we know in physics is always less, it has less deuterium than the water source it is. And this is what it is. God's Spirit hovered over the waters, if you open your Bible.
That's unbelievably fascinating. I just have to commend you on this. I would like to somehow read the Bible with your eyes at some point. That would just be
it's fascinating.
Amazing. Because I've been reading, actually I'm reading the Bible for my own curiosity, and Genesis I finished, and most of the way through, I did finish Exodus and started Leviticus. But for me, I'm not looking through a deuterium depletion perspective, and I ought to, because for me, it's a bit boring.
That's how it starts and that's how it finishes. So if you use Deuteronomics as your lens to read the text, you're going to see a lot of different connections and different level of connections. Now, what's really interesting is that that's how God identifies himself. And if you actually measure your own breath, the water vapor, the deuterium content of your own breath, it's also low in deuterium. So God's Spirit and your spirit, and God, as he positions himself as the source of life, is the same source of water as he identifies himself in the text. So practically, we are living creatures, and we can measure out almost like God's presence in our body, simply because our exhaled breath, the vapor, has lower deuterium than the environmental water. So practically, we can almost measure.
Mine was really bad. I was like 100. I wanted to ask you this separately. It's my pure selfishness again here, but are the tests accurate? and we got to get back to the Bible story, but I did a test and my saliva was like 150 and my breath was 153, or whichever's typically higher was higher. It was not good. And this was maybe 2 years ago now, but it wasn't
well,
good.
you need to look at your diet, what you were consuming those times.
Probably
Mine
too
was
many carbohydrates.
130. Huh?
Too many
Yeah, a lot of
carbohydrates.
carbohydrates. So if your diet is not kosher, quote unquote, you don't have to eat kosher diet, but you have to eat a ketogenic diet. That's just like described in the Bible. And I'm going to give you this example next. In the Old Testament, in the Torah, if somebody is thirsty and asks for water, they never give him water. They always give him fat, or they give him oil, or they give him actually sour cream to eat. So in the Old Testament, there's never, ever a human being would drink water that is unknown as a source. And they would rather feed them deuterium depleted fat to hydrate them, simply because that's the sure thing. Then you don't introduce deuterium through a liquid in your system. So practically, and this is fascinating simply because you would expect if somebody is thirsty, they would get water. That never happens in the Bible. They always give them fat to get them hydrated.
That's amazing.
Which is really incredible. And the third very important example is when you actually look at how agriculture starts, the second goes back to the second day, and it actually the dew, the water is rising from the earth, and that's how water and rain comes down. So this deuterium fractionation process in the rain, generating rain, is also described in the water. So our agriculture should be water vapor that is generated and fractionated from environmental water. So wherever you look in the Bible, there's always a kind of a deuterium depleting principle, which you have to look in details, but you can actually always recognize those.
Wow. So I'm guessing it's obvious here. The reason dry farmed wine is better than wine that is irrigated is because it's only watered with rainwater. So it's deuterium depleted wine. And so most agriculture in the world is irrigated. So it's done with river water that is higher in deuterium. But if the river water is coming from snow melt or from rain, isn't the river water technically fractionated? Or if it's coming from a spring,
it is
spring water fractionated?
And it is, and that's why they provide and they contribute. That's why they believe the river of Ganges, which is in India, has some healing powers. The river in, for example, in France, there's a water source which is high altitude, and people use them as medicine. Practically, it's just deuterium depleted. And you're right. Some water source, if they are from high altitude, glacier type of water or melts, they are low in deuterium and they have some healing powers. So because of their deuterium depleted nature. So you just need to look at the deuterium content of, for example, the water source, and then you can tell how much healing power they contribute to it, or potentially what's the history of it, simply because the deuterium depletion is always coming handy to deplete deuterium if the water is deuterium depleted.
Okay, so I think we've gone through an hour and a half and a little bit more of all of this very interesting theory. I want to get straight into, because we'll probably do another podcast in the future as well, but I don't want to keep you on too long. I want to get into the meat of it now. Like, I want to be convinced by the end of this call that I should never eat carbohydrates again, basically. And so I'll just say for the listener here, if you listen to some of Dr. Boros's other podcasts or talks, you'll learn that carbohydrates are higher in deuterium. And so the main source that humans get deuterium in our body is from water we drink and carbohydrates we consume. Is that correct?
That's right.
Generally speaking.
That's correct.
So your dietary you advocate for a ketogenic or basically a low deuterium diet, right? So that would be essentially what people know as ketogenic. So could you explain first Like, why do carbohydrates have more deuterium? Is it because, they're made from water, from rain, or from irrigation that hasn't been fractionated as it went up through the animal kingdom?
Carbohydrates are synthesized. The original carbohydrate synthesis patterns are related to fruit production. The plants, they produce fruit and they produce carbohydrates to make them sweet. Sugar. These are sugar bowls practically. And the fat or the ketogenic diets, they are produced in plant cells as, again, in their mitochondria. So it has to be deuterium depleted. Now, this is the main difference between carbohydrates and fat. Fat can only be produced by fatty acid synthase, de novo, and fatty acid synthase can only use citrate products. And citrate synthase only exists in mitochondria. And mitochondria is deuterium-free in nature. So every fat or the fat source that you use has low deuterium simply because they have to go to mitochondrial metabolism in the first place. And that's the same in plants. So citrate synthase of mitochondria and the citrate shuttle, which provides this cytosolic or cytoplasmic malonyl coenzyme A, that's the source of fatty acid synthesis, but it has to go through a deuterium depletion through mitochondrial processes in every species. That's why natural fat is always lower in deuterium than the carbohydrates, because carbohydrate synthesis does not require mitochondrial processes.
Photosynthesis is carbohydrates generally?
Just photosynthesis. Well, photosynthesis provides the hydrogen, and carbon dioxide is brought in to make an organic molecule. So hydrogen is attached to a carbon skeleton. And since carbohydrates are not required to go through mitochondrial metabolism, just like fatty acids from this particular source substrate, which are 4 carbon first, and then it's glucose. Even then, when glucose is used for fatty acid synthesis, it also has to be depleted in mitochondria because it has to enter the mitochondria for fatty acid synthesis. So there is no fatty acid synthesis that can actually avoid or side mitochondrial processes, but carbohydrate synthesis is, unfortunately. So carbohydrates are, because they are the product of a non-depleted chemical synthesis process. Carbohydrates as sugars, they are actually purposefully loaded with deuterium because actually that provides the sweet taste of fruits, and the fruits carry the seeds, and this is how trees propagate themselves. The animals eat it, their microbiome start junking up on benching on deuterium. Those mitochondria or those bacteria retain deuterium for their constant growth. This is how they wrap the seeds of the fruits, and they just poop it out, or they just drop them a few miles away from the source that they ate this high deuterium sugar. And this is why sugar is not really our food source, simply because sugar is addictive simply for animals not to be able to resist it, meaning that the tree's propagation strategy uses this addictive high deuterium carbohydrate source to make these animals crazy about it and eat as much as they can to disperse those trees' seeds and propagate them as efficiently as possible. Humans not necessarily, and humans should not eat sugar or should not eat fruit simply because it has too much deuterium for us. We actually eat, and if you look at anthropology data, our development, our adaptation started with eating bone marrow. And they know this because they found very old bones, 3.5, 4 million, almost 4 million years old bones in ancient rivers and lakes, which were opened by a tool, meaning that the caveman or the prehistoric man, they started eating bone marrow simply because it was a safe food source, and they started eating deuterium depleted natural fat. And this is why our brain developed, because we actually exposed our bodies to less deuterium by eating fat, and we could use our brain cells and we could use those chemicals to produce neurotransmitters instead of repairing nanomotors. So we took an advantage by adapting to a food diet or ketogenic bone marrow based diet that lasted almost like 2.5, 3 million years before agriculture started, before the cities were formed, before actually we could cultivate our own food, and we could start growing plants and grains and start eating deuterium again. And that's when the diseases started. That's when the problems started building larger human communities. And this is when the agricultural processes started, and this is when chronic diseases started.
Okay. Yeah. I wanted to ask you, how did we go wrong? How did we
It's
really
agriculture and growing grains. Switching
growing
from a
grains?
bone marrow, uh, bone marrow was so important and it was so safe to eat because predators were not interested in bones simply because they didn't know how to open them. They didn't have tools, but the prehistoric men did have tools. So they knew how to get to the bone marrow part of large animals and how to open the skull, the cranium of those big plant-eating animals. If you look at, for example, a mammoth, if you look at the brain of the mammoth, that's at least 20 kilograms of bone marrow. You can feed a whole family with that. You just need a tool to open it. So practically that's what predators couldn't do, but the prehistoric men could. And this low deuterium ketogenic diet gave them a advantage of developing some other organs, for example, brains and small joints. So more and more social functions and more cognitive functions were appearing based on this ketogenic diet. It was so important for them that if you look at 400,000 years ago, if you look at caves around Tel Aviv, they found caves where actually they had bone pieces where the skin was actually sutured back onto the bone simply because they conserved bone marrow for their travels and for their hunting trips. So they were actually
Wow.
carrying their own bone marrow for up to 8 weeks. 9 weeks, they could conserve bone marrow as their food.
Wow. That's fascinating. So
and they also cut off the bone edge with the cartilage. And if you look at ancient writings, the most valuable food item was this cartilage because of the bone marrow and because of the broth that they could do. They could make low deuterium broth that they could make from it, and that was actually one of the most valuable food items for them.
Now, for the broth, they probably had to use some kind of environmental water, though, didn't they?
Not necessarily, because if you actually put these cartilage and bone species to actually cook and boil, thicker that it is, more like a jello kind of product, this is what they consume. They didn't dilute them simply because they didn't want to have this diluted up. So this was more like a gel for them.
I see.
So it was
Wow.
they were not drinking it; they were eating it as a food and water source.
Yeah, that's amazing. So I'm going to take a slight digression before we continue down the path of human evolution. We talked about how fats always have to be made through the mitochondria, right? So, and carbohydrates don't. And so carbohydrates take on, it's not that they necessarily take on more deuterium. They're just taking on the environmental deuterium. It's that it's not being fractionated, correct? That's
right.
why it's higher.
Right. That's
so,
correct.
And so we are, our complexity is dependent on the lower deuterium fractionation. So we need, or more fractionation, lower amount. So, okay. So we need the fat, ultimately speaking. So what about the only plants that I'm familiar with that produce fat, obviously I'm pretty sure all plants produce some amount of fat, not much, but like that we eat: coconuts, avocados, olives, and maybe like the palm for palm oil. And maybe now, of course, they do like refined, rapeseed oil, canola oil, which you've talked about how that's like the highest deuterium food practically, like margarine. But for the ones, well, let's actually talk about that, briefly. Why are the fats, omega-6 fats from highly refined seed oils, ridiculously high in deuterium, whereas like the fats from those few other plants, avocados, coconuts, and olives, as far as I know, lower in deuterium, or are they?
Yeah, because they actually process them industrially. They actually use hydrogen gas to saturate them with hydrogen. So the way they control the oily and the fatty components in those like cooking oils, they actually use industrial hydrogen gas with unknown source of hydrogen, and they actually saturate these oils or these like margarines that are like plant-based fat. They all produce fat, plants. But when you start adding hydrogen with unknown deuterium content, some of these hydrogen gases that they use are environmental. They have higher deuterium content that we would expect. Some of them are very, very high. For example, if you look at potato chips, they have 160 ppm deuterium content. So the industrial deuterium saturation or hydrogen saturation process is actually a deuterium loading process into these foods.
But so olives, avocados, and coconuts are safe. They're
Yeah,
very
because
good.
they are natural source. They are natural plant source. They are not saturated with hydrogen. If you start saturating them with hydrogen, you end up again with an undesirable fat source. But as long as you eat them at its natural state, then you are safe. Yeah.
So what about like, for example, unsaturated canola oil or soybean oil? Most people in the health world have a strong agreement that these omega-6 fatty acids that are refined at a high heat, they're not necessarily hydrogenated and turned into like the trans fat like margarine, but they are an omega-6 that's generally considered really inflammatory. Is that related to deuterium, or is that a separate effect?
Well, as long as you don't saturate them with hydrogen, as long as you don't try to make them more like butter type or more like fat type from the oil stage or oil phase, they might be good. They might have low deuterium after all, so they might have desirable effects. But I don't really know how to trust these products simply because I don't know how they are prepared. I don't know what the source is. Yeah. I don't really know what is for example, canola oil. You can eat canola seeds. That's the safest way of getting canola oil in your system. Once you start extracting fatty acids, once you extract with organic solvents fatty acids from a fat source or from seeds, they usually squeeze them out and they extract them industrially in the industrial setting. What happens is you don't know what you end up as the end product, which oil fraction or which oil type you extracted from that particular sample, and what was the original deuterium content of that. What was the agricultural process that was producing that particular plant? Was it natural? Was it irrigated? Was it GMO? Was it water irrigated? Was it? Did they use pesticides? Did they use glyphosate? Did they use? There's a lot of agricultural processes that already contaminate your food source with deuterium. So anything else they do to it is just not desirable.
So when many people in the health world, many people argue that if your omega-3 to omega-6 ratio in your cells, in your body is too high, or I should say omega-6 to omega-3, then you're going to have, higher rates of many different diseases. It's in the paleo diet world and ketogenic diet world, there seems to be a consensus that especially refined omega-6 oils like canola, cottonseed, soybean, these are all very bad, and they're industrially pressed, at really high heats, and that causes, I think, oxidation of the fats. What is from your perspective, how's that an issue? Like the oxidized omega-6 fats or omega-6 fats in general in excess?
Again, we actually discussed this in Neuro-Oncology, the journal Neuro-Oncology. Actually, Dr. Kruse read this paper because when we spoke first time when he called me, I did send this paper to him simply because we argued this particular phenomenon, how industrial food source in general and how the agricultural and how the irrigation and the glyphosate and the pesticides and the weed killers and all the industrial processes that are involved in food production Oxidizing these fatty acid species don't seem to change deuterium content. Yeah, they change their absorption, it changes their transport, they change their membrane transport, and so on. So putting all these scenarios into one particular argument of how biochemically they are natural, or how natural source as fat source for our body, it only you can only make very limited predictions of what the end product deuterium content will look like, simply
I
because
see.
if the source is not clear, the agricultural process is not clear, the GMO process, because GMO is nothing else just kicking out a few genes which deplete deuterium for the plant so they grow faster. So practically all GMO processes is actually loading these plants with deuterium. So any fat product that you produce from those plants, oxidized or non-oxidized, may have already higher deuterium. So the only good source of fat is practically animal fat or plants that are actually used and grown in their own natural environment, without any additives, without any agricultural process, without anything that interferes with the plant's deuterium depleting potential.
So that's so interesting. If we're talking, for example, about like a cow that was fed, grain most of its life. I mean, a lot of cows in the United States, that's not good. So the fat of that cow and the protein, we didn't really talk much about protein obviously yet, but is the fat of that cow, like if you said normal saturated fat's like 105 ppm and a potato chip is 160, how high do you think the fat of
it's by 130 ppm. I think we measured grass fed versus grain fed or farm raised cows. There's about 15-20 ppm difference in
wow.
fat.
Okay. So it's probably still better in your eyes to eat like a grain fed cow than it is to eat a Lay's potato chip?
Yeah. Well, as like good as it is, it's just a good option, a better option. It's not good, but it's a better option than just to eat, high deuterium containing potato chips.
So then this is again, this is more almost like physics and circadian biology. Dr. Kruse, I have two things from Dr. Kruse I want to ask you about. So he didn't ask them, but I'm just wanting to ask them. So for example, with avocados, right? That's like it's a fruit. And coconuts and olives. I don't know if olives are considered a fruit. I believe they are. But so these are seasonal, right? And so because they're low in deuterium, you say they're safe and healthy to eat, but are you concerned about the concept of maybe eating something like out of season? For example, Dr. Kruse argues if you're eating even avocados out of season, there's some sort of biophysical mismatch because the light in the electrons of the avocados is mismatched from the light of your current environment. So he stands pretty firmly behind the idea of eating a consistent seasonal diet no matter what. What do you think about that? Do you think it's maybe not so relevant or could be?
Yeah, that's a very fair argument, and simply because of the photon pressure and the resonance scales that you look at deuterium depleting potential in plants, and as you adapt to those plants, practically you have to expose to the same photon pressure and same resonance scale, simply because you are living in the same fauna, in the same environment, practically, meaning that your seasonal food and your photon pressure, your sun exposure or your light exposure, and the same of the plant, you deplete deuterium for each other pretty much in the same fauna on a seasonal basis, simply because you depend on each other for propagation, for food source, for propagating plants, eating their fruits. Those are animals mostly, but they are also exposed to the same sunlight and photon pressure or photon resonance scale, simply because if you look at how important deuterium and hydrogen resonance is, because actually light, that's what light does. That's how light breaks water. Practically starts resonating the proton on the oxygen, and it resonates with enough strength that actually protons will broken off from the oxygen, but deuterium does not break off. But if the proton pressure is high enough, the photon pressure, the light intensity, then even deuterium can break off from the oxygen. So there's less efficient deuterium discrimination in summertime when the sunlight is more intense and longer exposures. So practically, this is how your skin has to be exposed to sunlight as the plant that you are eating in their natural habitat without agricultural processes in the same season, because your deuterium and hydrogen resonating potentials with the same sunlight actually make sure that you can deplete deuterium, you can control for deuterium in your biochemical processes just as efficiently as the tree which you are standing next to it, and you're going to eat those products very soon to actually supply your bodies with hydrogen and discriminate against deuterium. So these systems work together under the same umbrella of photon pressure and light intensity and length or exposure. So you have to be careful, and Dr. Kruse is right, you have to be careful of your season, what you eat, what seasonal food you eat, and where it is shipped in from, what's the location of that food, and if there was any agricultural process or processes involved in producing those food items that you eat. These are the most important guidelines. These are the most important elements, and light has a great deal of controlling deuterium discrimination in the during the photosynthesis process, and deuterium discrimination while you're metabolizing and carrying protons and hydrogen in organic food. For example, cholesterol. So if your cholesterol has high deuterium, then you cannot make efficiently vitamin D simply because deuterium bonds on the cholesterol ring. It doesn't allow resonance enough to break those bonds that make actually vitamin D from cholesterol, because it all depends on resonance. So if you eat a cholesterol source which is high in deuterium, you won't be able to make vitamin D from them. And if you eat a vitamin D source that is a supplement or coming from a different region, then it may be loaded with hydrogen, may be loaded with deuterium. As a result of that, it's not going to resonate with sunlight as efficiently. It's almost like sunlight, sun exposure, and the time that you are exposed to the sun, kind of the common denominator of how the biofauna, how the species interrelate metabolically with each other, and that's determined by sunlight. And you have to be in the same environment, in the same season, to kind of get to the same common denominator, how much deuterium you can handle, how much resonance you can handle, based on deuterium and hydrogen ratios in the food and in the environment that you obtain through water and food. So practically, light controls all these elements in an interrelated species overarching manner that actually is true of all the biosynthesis, the green biomass around you, and oxidizing, the burning, the energy producing animal fauna, which actually burns organic material and provides water and the droppings for the plants to grow. So practically, or partially. So practically, this is a very important common denominator: the sunlight, the sun exposure, in the same biofauna, to actually, as a denominator, to bring everybody to the same level as far as deuterium discrimination goes, and hydrogen resonance, energy production go, after all.
That's fascinating. I'm going to be back in half a second. Real quick. Just grab my... My computer can manage to go through multiple charges when I when I do this. So I have a charging bank that I had to power up. So thank you for explaining that to me. Sure. I'm very curious when it comes to. I am very curious when it comes to the season. Okay, well, we talked about the season. So basically, if I'm living in, for example, where I am right now in Idaho. I'm here because I was in Costa Rica in a strong sun place, but the coronavirus struck. And so I came here to be with some family and aunts and uncles and so on. And in the winter and even now, the only food that's really like around is elk. There's really not much plant growth. So it'd be like fasting and elk meat and deer meat. Is that kind of the way to go in the winter? You think the native populations at northern latitudes and far southern latitudes would have essentially been eating fish and meat because there's nothing even growing from a plant perspective?
Yeah, so this is how Sergio helped. Yes, indeed, it's elk. It's seasonal plants or many parts of the elk that you are actually have interior organs. You have meat, and you have also bone and stews and what you can prepare. And there are other deer. There are other rabbits. If you actually go out and look around what you can eat in your local environment, you're going to see a very diverse seasonal and very interesting kind of options of how you can deplete deuterium most efficiently. What actually you should be eating, and this is maybe the most interesting scenario, you should be able to look at carcasses of the predators or the animals that actually are in your local area, and you should eat their bone marrow for two reasons. These are easy to get. You don't have to fight, and you don't have to chase them. They are already dead, and the predators ate all the meat. You can just actually, like the cavemen did, you can just actually collect the bone, make them stew, make them broth, or make them just open those bones and eat the bone marrow, because they don't get rotten, because they are actually don't have enough deuterium to grow bacteria. So fat is really a safe source of food because it doesn't have carbohydrates and it doesn't have bacteria in it. They are confined to a bony compartment, so you can actually carry them. It's the most practical food. So this is your optimal food source, is practically the bone marrow of the large plant-eating animals.
Yeah.
And you just have to remember where those carcasses are. That's what the cavemen did, and this is why their cognitive function, they didn't have to run, they didn't have to compete, they didn't have to risk their life to get into a pack of animals that are waiting for meat. They could actually just go and eat the bone marrow and supply them with bone marrow with themselves, supply themselves with bone marrow, which kept them alive and kept them evolving and adapting for about 2.5, 3 million years. And again, when you look at your options and you look at a Deutenomics kind of guy, then you can, an anthropologist, then you understand better what your role is in that particular food chain. And the safest is practically just to eat the fat. And the plants, the seeds, they also have fats. And over time, you learn how to get into a ketogenic diet, which is your natural state of existence. And this is what sleeping does practically. It puts you into a natural ketosis, and that's how you need to keep and continue daily on. And for that, it's enough if you just collect bone pieces and eat them on marrow.
Wow. So the second thing related to Dr. Kruse that I've learned from him, and I want to sort of challenge you with this, and I'm very curious for your perspective, is his belief and that of some of the researchers he presents argue that the primary driver of the evolution of the ape into the human was a consumption not of bone marrow, but of shellfish and the high nutrient dense omega-3 rich shellfish, and that this explains why we have the brain, which has so much DHA, omega-3 in it. So I'm curious what you think about that theory, and is it a competing theory, or could the two have come together? Could they have worked together? I'm very curious what you think about that theory of brain evolution, that it was seafood and shellfish driven.
Well, in my opinion, it is practically the way how we can collect more fat and how we can prepare more fat and marrow-based food and broth once we actually learn and once we are able to use our hands differently than the apes can. The only difference between an ape and a human being is practically you can oppose your fingers with the rest of them. You can actually hold things. If you look at apes, they are not able to oppose their thumb against the other fingers. No ape can do this. They can actually hold on to trees like this. They cannot oppose and they cannot hold tools. They cannot make final food preparation processes. They cannot actually work on, for example, skills like leaving signs. They cannot really disassemble small bony parts. They cannot really make tools as part of their food obtaining principles. So practically what I believe between the apes and the humans, the most important thing is that they were able to keep eating bone marrow when the apes had to be seasoned in a seasonal basis. They had to stay with their plant-based diet. We do know that chimpanzees are carnivores. We know that many monkey species are actually carnivores, so they eat both plants and they also eat meat occasionally when they can get it. But practically they have to compete as predators, they have to compete for food source. So for meat source. Humans, they don't have to compete for bone marrow. So because with these fingers, we are able to hold stones, rocks, and make tools that actually can open very tricky body parts of animals that have bone marrow in them. So this really fine ability of movement of our hands, which I believe come from very ancient times, in prehistoric humanoid times. I think this is very helpful to actually prepare certain food items, mainly broth, and we could actually carry and grab things. We can actually carry bones. We can actually cut them. We can actually use tools to prepare certain fatty parts of the bone and cartilages to make them a variety of food source. I'm not saying it's a different food type, but it's the variety of food using the same source, because we are able to manipulate them further using various techniques and various ideas. So I think after all, since we stayed with the low deuterium and we can stay with the low deuterium natural bone and cartilage and natural fat eating properties or habits, we were able to develop further or adopt further based on this very low deuterium diet, which apes cannot really afford simply because they have no ability to use tools the way we can use tools. And that's been going on in the last 2.5-3 million years. So I believe that staying with the low deuterium ketogenic diet that was obtained from various leftovers of animals, mostly bone marrow and brain, and being able to carry that on under various environmental circumstances and seasons and also locations, we could populate with this ketogenic food eating items, fat eating items, bone marrow. We could populate the entire planet. Apes are very limited because they have to live on trees, they have to hide, they have to follow a certain lifestyle, and they can only eat plants and occasionally they can eat meat, but they cannot really eat bone marrow simply because they don't know how to open the bones. We did, because we can actually hold stones and open the big bones.
So is shellfish and seafood, is it deuterium depleted? Like,
yes, it is deuterium depleted simply because if you look at the fish, they eat organic material and they oxidize organic material pretty much the same way we oxidize them. into low deuterium, and some fish is very fatty, like salmon. So it's a good source of low deuterium fat. The bottom feeding, like shellfish, the deuterium content is less predictable because they feed from the bottom. So it's not as, they are not predators like most of the, I would say, fish. Bottom feeding fish or freshwater fish are less predictable as far as their deuterium source. They are low in deuterium or lower in deuterium simply because they are animals. And because they belong to the animal kingdom, so they eat organic material and they have to use their mitochondria to produce their own metabolic water because they are unable to synthesize, they are not able to perform photosynthesis. So they always have to be deuterium depleted simply because they consume organic food and they burn it into metabolic water in their mitochondria.
Okay, so just a couple more questions to sort of get towards the conclusion here. The overarching takeaway is for people who want to effectively deplete their deuterium is to avoid carbohydrates for the most part or entirely and eat a ketogenic diet. So I'm curious about, and I listened to your podcast with Ari Whitten, The Energy Blueprint, and I thought that was a very great interview. You guys got pretty into it. So what about, there are cultures, for example, where there are super centenarians, people living past 100 on a consistent basis, where, as far as my knowledge goes, they eat some regular amount of carbohydrates, so like, for example, in the Nicoya Peninsula in Costa Rica, they are eating a regular diet of rice and beans, and in addition to rice and beans, they eat meat and fat as well. So it's not exclusively a high deuterium rice and bean diet, but it is pretty high. And I think there are cultures all around the world that are these super centenarians where they weren't exclusively ketogenic. In fact, they ate grains, they ate these. So my curiosity obviously is, how were they able to be super centenarians and live so long and seemingly healthy lives while eating high deuterium? Like, in other words, how are they either A, living long with high deuterium levels somehow, or B, are they able to deplete it through some environmental factor?
Yeah, that's the scenario. They have to be able to deplete it. They have a microbiome that depletes deuterium from them. You need to look at their stool. So you need to look at the amount of stool. Their stool is probably larger. It's more volume and it's more deuterium packed. And you have to look at their epithelial cell shedding. You have to look at their skin shedding. So you have to, because we deplete deuterium many different ways. We deplete deuterium through the stool. We deplete deuterium through the skin. Your skin actually produces and depletes deuterium on a constant basis simply because you produce keratinocytes, especially when you're exposed to sunlight. So you actually deplete deuterium very efficiently in your local environment once you encounter the appropriate microbiome for it, and you're able to stay in your local environment and not ship in food with unknown deuterium content, but you can adapt to your deuterium environment, then you know how to deplete it. And you just have to eat the same thing, and that will actually keep you healthy as long as your deuterium depleting potential. And these human species, they give these bacteria to one another because they actually in close contact with their offspring, simply because they carry them on their body. They actually get in contact with their stool and everything. So practically they are very efficient in providing one another the deuterium depleting microbiome and also the deuterium depleting lifestyle. And you have to investigate them, not or just what they eat, but also how they poop, how they are exposed to light, how they shed their skin, what their skin color, what their daily routine, how much water they drink, these things, what the water source, and what's the deuterium content of the food, of the rice that they grow in a non-GMO environment. Because again, plant food can be deuterium depleted if it's natural grown, meaning that it's not GMO or not agriculture, it's not an agricultural product. you can actually be safe on a relatively carbohydrate-rich diet if the carbohydrate portion of your diet is deuterium depleted, and that's the case with plants, which are not GMO plants. So if you look at some papers that discuss the deuterium content in carbohydrates, for example, the fifth and the third carbon of sugar in beans, for example, which are grown in natural environment, they are actually pretty depleted of deuterium simply because they use the night cycle when they use their chloroplast as mitochondria. And if they produce sugar based on mitochondrial products, then their mitochondria and their carbohydrates are deuterium depleted as well. So they are safe, even though they eat carbohydrates. It's not fruit-based. That's what is most important. It's actually grain-based, and the grain can be low in deuterium based on the metabolism of the plant. And we published a paper regarding this in Metabolic Cell, which I'm going to send you after the podcast so you can actually look at these. And also I'm going to send you a list of publications about this quantum destabilization of water, because once it's destabilized, then you can actually follow up with some biological phenomenon, mitochondrial processes that you want to explore to take this story a little bit further. So as we work, we always kind of incorporate the newest, most efficient information to explain mitochondrial functions. And both the plant-based low deuterium carbohydrates are an important piece of the puzzle in this context. And also this quantum destabilized water is also very important, because this is how we understand proton function in mitochondria and how bad deuterium is not being able to participate in this process.
Gotcha. I would love to, in a future episode, I'd like to talk more about that and how, I'm assuming a healthy person, if someone's like just healthy, right? They don't have any sicknesses and they live in a natural environment, which is pretty rare today, I would say, just because of the modification of the food supply and the lifestyle that's always indoors and not out in the sunlight. It's rare to find someone who's, I think, really healthy. But in that case, maybe they can have seasonal carbohydrates if they are non-GMO'd seasonal carbohydrates.
So exactly, and it's not fruit.
And so you recommend never eating fruit, even seasonally? You would say it's just
seasonally. You can eat fruit as much as you can get in your local environment, but you won't get much. And I'll tell you why. Because fruit are so sweet that it's so competitive and it's so addictive. By the time you get to the apple tree, the birds, the squirrels, the animals that can actually get to it faster than you can, they already ate them. Or if they have fallen from the tree, then you are out of luck simply because the wild boar and the elks will eat it. So in a competitive animal environment, I'm not talking about going to roughs and getting a kilogram of whatever. If you compete with animals in your own environment, you're not going to get much fruit.
You're not going to get much fruit. So fruit is like the bottom, like the top of the pyramid. Like avoid it as much as possible. Don't touch it. Yeah. So then what about grains? Like non-GMO
grains? Grains nowadays they are all GMO, because you can only get GMO grains. But if you actually look at corn, just give you an example. If you find wild corn, you know how big that corn is? It's small as this. It's not a GMO. It's really not a huge food source. You still have to look for fat to energetically balance your
system. It's not a natural food source, right? Yeah.
It's a natural.
And that's the key.
That's the key, exactly.
I have upstairs.
As long as you eat.
I was just going to say, upstairs I have this organic, gluten-free bread source or bread that I got from my, health food store that my aunt has. And it's not health food really at all, and I shouldn't be eating it. It's like, yeah, I can't, gluten I won't eat because I actually react to it. But now I'm thinking like, this is not something I should be eating because I already knew this and know this intuitively. It's kind of like a treat in a sense, but it's not a good treat. I should treat myself to bone marrow or something like that, you know? Because there's no way I could scavenge enough grains myself to make even a tenth of that loaf of bread. So
Yeah, again, we kind of misunderstand of what is plant eating or what is fruit eating. In nature, it's a very competitive process. We are kind of misled that you can get a kilogram of apples, or you can just like get 2 pounds of apple juice. You just go to Ralph's and get it. Now, in nature, it doesn't work that way. In nature, it almost like every apple is looked at by many species. It looks at by birds. It looks at by the wild boar. It is look. A lot of animals are looking at it and waiting for this sweet taste and the con, because it's very addictive. So that's why fruit eating is really not an option if you are in kind of in harmony with your natural environment and you live in a very competitive animal kingdom. And you can be the leader, you can be the smartest, you can be the most controlling whatsoever, but as long as you approach it from the natural, from the nature's given food sources, you have to compete very heavily. And the easiest to obtain and the safest to obtain as food source, and the most energetically most abundant as far as energy yield is actually the bone marrow.
Bone marrow. This is amazing. So that's all really, I appreciate you going through all that stuff so people have an idea of what's sensible to eat from a deuterium perspective. And my last question, and this might take us a little ways, but we can keep it brief, is related to deuterium depleted water. So, a podcast with deuterium wouldn't be complete without this. So, for example, if I were to be I'm totally, just like probably most animals in a sense, based on what you're describing, a carbohydrate addict. Like, I love carbohydrates, and I definitely need to not eat. I don't eat a ton of them because I'm aware of this. Ever since listening to that podcast, even when I did eat carbohydrates, I was still keeping it low, knowing that it's just not optimal. But anyway, so if someone in my, in this situation were to pound the carbohydrates, which again, clearly is not a good idea. It's just not smart, and then drink a ton of deuterium depleted water, just for a theoretical perspective, does that offset the effect? I'm actually not looking to do this, even though it might sound like I am. How does the water interface with the deuterium consumed from food? Because the deuterium consumed from food is going one place. That hydrogen and deuterium is going one place. How does that deuterium not deuterium, the lack of deuterium in the water affect the system?
Yeah, so there are a few biochemical reactions. These are reversible isomerases most of the time. Hexose phosphate and triose phosphate isomerases are replacing hydrogen and deuterium on carbohydrates. If you look at glycolysis, I have a few talks related to this, but you can actually use water as the depleting source of low deuterium carbohydrates or lactic acid first. It happens in the red blood cells because red blood cells utilize glycolysis to produce glucose to produce lactic acid, and mostly they need a 1,2-biphosphate glycerol to actually modulate the oxygen binding capacity of the red blood cell, the hemoglobin. So you can actually deplete deuterium on carbohydrates if you drink deuterium depleted water, but it's really truly not efficient because you suppress your mitochondrial deuterium depletion or the exchange of metabolic water with zero deuterium that can actually intracellularly in your body, in your host cells, they can actually, if the deuterium depleted water is not sufficient to deplete deuterium and carbohydrates, lactic acid mostly, then the Cori cycle that restores glucose from lactic acid in the liver still cannot deplete deuterium efficiently enough that your body cells, their mitochondria can produce the sufficient deuterium, low deuterium water and deplete deuterium from the remaining carbohydrates in your body or what you ate, simply because these reactions, they need a deuterium low substrate pool before you can actually go lower in deuterium. You cannot really count on your biochemical reactions in your red blood cells to deplete all the deuterium for you if you have eaten a high deuterium carbohydrate source food, which would take actually a lot of passages through red blood cell metabolism to deplete deuterium efficiently using deuterium depleted water that you drank, because that only occurs in your blood, in your blood vessels. Once you get to the tissues, once the glucose and the water got out to the interstitial place, they compete with metabolic water that is produced in your mitochondria, in your cells. And if you have too much deuterium depleted food, depleted water that you drank, then you, because of the low the ADH, the antidiuretic hormone level, your mitochondrial functions will be altered. So simply too much water intake is not desirable simply because you disrupt this natural antidiuretic ADH or oxytocin, vasopressin type of metabolic regulation on your mitochondrial functions. And you need to look into this before you actually formulate additional kind of reasoning points or additional ideas, because the water intake is a problem. I would not drink water under any circumstances if I have to do it because I ate something that is too high in deuterium. I would not eat the too high deuterium carbohydrate source, so I don't have to follow up with water intake, because actually that disrupts some of your hormonal regulations of energy production.
That's, I think, possibly the most amazing answer of the whole podcast, because I mean, sometimes, you know, I know you as a person, sometimes it just slips from my mind that you're a professional biochemist. So the fact that you're able to explain that so well is amazing. So again, I didn't understand all the details, to be honest there, but what I do understand, and I get more than what I'm going to say right here, but basically it's obviously a bad decision if I eat external, if anyone eats external carbohydrates in particular. Again, we're talking modern carbohydrates that are probably high in deuterium, especially fruit, especially sugar or anything that's refined, you know, excluding maybe high quality beans and maybe high quality grains, if that's even possible. But let's just lump them all together. You consume that, you're loading your body with deuterium that your body's going to try to get rid of through systems we didn't fully describe, but you know, you implied them many times. And I don't think the biochemistry would have helped the listener or myself too much anyway, or maybe me, but not the average listener, right? So we try to deplete it, but we can't get so much of the deuterium out of the system that eventually a lot of it does go and affect our nanomotors, and that's not good. A lot of it goes and affects, DNA, proteins, because we just
and
simply
this quantum destabilization process, when the quantum destabilized protons are not available because they are replaced by deuterium, then your mitochondrial functions suffer even more.
So we become in effect less godly, like the vapor above the water, and more like the water itself, which is not good, not desirable. And I know that's a metaphor some people won't understand, but it's very useful for those who will.
You lose the spirit.
Exactly. We lose a lot of the spirit. That's very amazing. So I guess, because I'm always in my mind looking for the excuses of, I want to eat the carbohydrates, just like a true addict would. But it's truly just, if I love talking with you.
It is an addiction.
Oh yeah. I love talking with you, Dr. Boros.
No question about it. Yeah. Sure. Thank you so much.
Yeah. I just want to say, cause my intuition every time I talk with you or even watch your talks or think of you, even, I just think, oh my gosh, how much better would it be to just be ketogenic? And then in my mind, for anyone listening to this who's just thinking, oh, but I love my gluten-free toast, or I love my bowl of oatmeal, or I love my fruit. Although I think fruit isn't something a lot of people truly base their diet on. It's more like the grains and the refined carbohydrates and that sort of thing. There are people who base their diet on fruit, like Steve Jobs, and obviously it didn't turn out too well for him. But anyhow, all that being said, it's just like,
I think there was another guy, what's his name? Krushner?
Ashton Kutcher.
Ashton Kutcher. I think he was eating fruits for 8 and he ended up in the hospital. So just like, so yeah, you have to, again, you have to try it outside in your environment just to see what you would eat and what would be available for you if you just sit on the back porch and just look not the refrigerator but the other way, just towards the forest where all the animals are and all the plants are, all the trees, and look at that competitive kingdom or animal kingdom that if you have to participate, your diet would be very different and you would have a much healthier life as far as.
And that's like the idea of the paleo diet, but not a paleo diet ridden with carbohydrates, more like a ketogenic paleo diet. So, and then taking the water maybe would be good for someone who's absolutely not going to change their diet no matter what. It might help them marginally, but if I'm committed to my health, it doesn't even make, based on what you're telling me, it wouldn't even make sense for me to go ahead and do the ketogenic diet and the water. It would be better just to do the ketogenic diet. Or would it be better if anytime I drink
again? Yeah.
But if I ever drink any water, which I'm probably not going to get to the stage where you are of not drinking any water without some improvement in my mitochondrial function and deuterium depletion, although I could always just drink olive oil, I guess, if I get thirsty and try it. But if I am drinking water, would it at least be better that it's deuterium depleted water for the optimal results, would you say?
Well, if you are thirsty and you feel like to drink water, then you should drink rainwater, which is deuterium fractionated, and it's cleaner. You should drink rainwater, and you should drink just as much as necessary just to kill your thirst. These are the guidelines.
This is amazing. I think you have, this has been 2.5 hours. You have answered a lot of interesting questions. I think that the biblical anecdotes and analyses, I should say, are fascinating beyond imagination. And I think if you ever write a book, have you thought of writing a book, like a public book, not a peer scientific academic
Actually,
article book?
I'm finishing a medical Deutenomics textbook, which will be available in the summertime. I do have classes in my Laszlo G Boros.com website where you can actually follow up with many of these topics. I talked about destabilized protons in October at the third deuterium depletion conference in Budapest. That's a full talk. I can send that to you with references and experiments that address the same issue. We took it to the mitochondrial level, the stabilization of protons. And so for that reason, it's just a lot of material is out there now. It's just kind of, you have to, in a more in a exploring kind of exploratory mind, you just have to look at and pick out those topics that are interest you, or you just take any of my courses and you can actually get some specific information related to these human organ type level deuterium depletion and diagnostics and therapeutic potential. Simply just give it as a good biochemical solid information that you can trust your body is gonna make the best out of it if you eat the right food, after all, knowing what you eat and why you have to eat a certain way. So it's all deuterium depleted after all. Stay away from water as much as possible. Restore your ADH, antidiuretic hormone secretion that improves and helps your mitochondrial and nanomotor functions. And after that, I would doubt if you would ever get sick or have any kind of population disease.
This is fascinating. This is just amazing. So one last thing is, if you're not planning on it now, I highly recommend doing a lecture just about the relation of the Bible or the Torah, Old Testament or New Testament and deuterium. Or if you have no plans to do that, I would definitely want to do a podcast just about that.
We do have a website for that. It's called itszA.org. That's actually Bible studies or ancient writings and Deuteronomics. We started that already. I actually gave a talk about this in Hungary in English. I can send you that lecture. And also, if you plan or you want to talk about those, I'm working with a rabbi from Jerusalem who is part of the Orthodox Union of Rabbis on this topic. And I'm working with the chief rabbi of Hungary, Dr. Thomas Rona, who we actually discussed these scenarios. And it's a different level of understanding the Torah and the scriptures. So we are adding a significant kind of health, strength, and human prosperity, and mental and cognitive functions, and so on, of how that can be kind of fished out and how that information is available in ancient writings, including the Torah. So I'm writing I'm working with people and rabbis on this particular issue because most of those texts are written in Hebrew, so we have to kind of talk to scientists and theologians who actually speak Hebrew. I don't speak Hebrew, and I'm not Jewish. So for that reason, I have to work with these people. I'm very happy to work with them. And in the future, if you plan to cover this topic, then you can just, go at it.
Oh, I would definitely like to schedule a podcast to talk about this in the future. And we didn't talk about the things. There's many, many questions, but how sunlight affects deuterium depletion in future subjects. So anyone who's listening, we might be able to talk about these, how melatonin and sleep really at a detailed level affects deuterium depletion, specifically melatonin, because, I sell blue light blocking glasses, and I'm sure it's all connected. I'd love to know how. I'd love to know your theories, if you're familiar with Dr. Douglas Wallace's work about mitochondrial heteroplasmy and that accumulation of damaged mitochondrial DNAs. And of course, deuterium must play a role in damaging those mitochondria and affecting the heteroplasmy. I'd love your perspectives on that. On if you're familiar with the biochemist Gilbert Ling and his work, I'll send you some.
I haven't heard of him yet.
Yeah, I'll send you some information as well. But we could have some great, interesting conversations further, and fumarate hydratase and how deuterium is relevant in the blood and how it relates to epigenetics and where is it needed in more detail, and how does that process work if we're trying to avoid it in our body. Could deuterium depleted water hurt a child if they're in development stages and they only drink deuterium depleted water? Anyway, that's all stuff for another time, but things that could be very interesting. So I just want to say thank you so much for taking this time, Dr. Boros. This has been a phenomenal conversation. I am going to go to my refrigerator and freezer after this and give everything that I should probably throw it away, but I'm going to give it to my family members who will eat it. All carbohydrates and anything that has any fruit or carbohydrates in it. And I will. Yeah,
just think of you as you are outside somewhere competing for a food source, and eventually the only thing safe you're left with is bone.